Okay, I'd like to thank Kadina and Mersha for the kind invitation. And so I will. And this is, I need to stop at 12:30. Yeah. Okay, great. So wherever I get to, it won't really matter. So there's, so definitely, I know we're all tired. Please ask questions. If there's something wrong with the slides, you say something doesn't look right, you're probably correct. So please point it out, okay? So I think I'm going to skip, maybe save the proof of this is not seeming to move things. Kadina, does this? I have that problem too. This is not seeming to move things. I mean, I can just push buttons. Okay. All of this is fresh enough. I thought this was going to be tomorrow, so just a quick review of notation. There's nothing here that I need to really say. Okay. So I did want to mention quickly a little more about the integrable kernel case that Ed talked about, this classical results for energy minimizers for when the Wiener constant is finite, when there is some measure that has finite energy, some probability measure supported on the set that has finite energy. So one exercise is to show that what's called the capacitary dimension. So when you work with Reese kernels, the value of S, where the transition is where you go from finite Wiener constant to infinity, that's called the capacitary dimension. That for a compact set in RD, the capacitary dimension is equal to the Hausdorff dimension of the set. Okay, so this is kind of a beautiful result. It means that this integrable, the previous result that Ed talked about, says that for a general fractal set, the n squared energy asymptotics are determined by the equilibrium measure. The equilibrium measure exists. Okay. Also from the results that the Reese kernel is strictly positive definite. That tells us that there's a unique equilibrium measure as long as the Wiener constant is finite. And so anyway, so for a general fractal set, we know the dominant energy asymptotics. There's an integral of equilibrium measure. Of course, that's often a difficult problem to compute, to know what the equilibrium measure is, but there's some constant times n squared. And then the next order terms are interesting, and we have a number of experts, including our organizers here, about the next order term that comes in. Okay, and we know that the limiting densities as n goes to infinity, the macroscopic behavior of the energy minimizers is the points are distributed according to the equilibrium measures. So here's some more pictures. I'm going to intersperse, especially before lunch, try to have a balance of pictures and math. So here's 1,000 points. When S is 0.2, so that's less. So here, this is the surface of this torus, which has Hausdorff dimension 2. It's a smooth surface. So our break here, the integrable kernel result will hold for these two. This will be the Coulomb interaction. You might wonder, maybe I just don't have enough points here for this one to see what happens as you go in. So here's 4,000 points. And we actually have investigated on tori in 3 dimensions, the equilibrium measure for the logarithmic case and for small values of S. And you can prove that, in fact, the supported equilibrium measure for, say, the log case is supported on the outer part. And this holds for general sets of revolution. Take a general set of revolution, supported the equilibrium measure of the log for the log kernel is always on what we call the outermost part, where you go out as far as you can from the axis of rotation along a radius. That part of the set of revolution is a superset of the supported equilibrium measure. Now, our work has really, I want to emphasize that for S less than D, the dominant asymptotics are for completely general, for example, fractal type sets. Okay. So when S is less than the Hausdorff dimension, we know the dominant asymptotics and we know the limiting distribution. When S is bigger than or equal to D, we call this the hypersingular case, because this is the case where the kernel is too singular to support, to have a finite energy measure supported on the set A. So when for Riesz kernels, when S is bigger than or equal to D, we know that the Wiener constant is 0. Also, when S is bigger, go ahead, Ed. Okay, sorry, exactly. It's the capacity that's 0. Yes. When S is bigger than D, it's also the case that not only is the blow up worse, but the decay is much better. And so local sums converge. That's the rough idea when S. So we're going to take more advantage of the short range nature of these kernels. So a lot of the analysis I want to talk about applies as we're learning to more general short range potentials. But for us, we require more structure on our set A. Okay, there's active work on energy on self-similar fractals. You can show that when S is large enough for self-similar fractals, that limits the dominant energy doesn't have a limit. There's a lim sup and a lim inf that separate that kind of reflect the fractal structure. Okay, so for us, we're going to restrict ourselves to a generalization of a smooth D-dimensional manifold known as a D-rectifiable set. So this is a term from geometric measure theory. A is D-rectifiable if it's the image of a bounded set in RD under a Lipschitz mapping. So if this is, let's see if this is, okay. Maybe I need to press harder. Here we go. Yeah, okay.
Sorry.
So a bounded set in R2, say, and then and it could be a complicated bounded set. It could be some kind of fractal, some kind of fat Cantor set inside here. And then we map it, say, into R3. So this is supposed to be with some Lipschitz mapping. Of course, this could be a mapping onto something with cone. So anyway, this is called, this would be, in this case, we're mapping from R2 into R3, and this is the 2 rectifiable set. Just by taking phi to be the identity, any compact set in RD is derectifiable. So that's a triviality. To show that a smooth d-dimensional manifold embedded in RP is derectifiable. It's not hard. You can go to charts and move things apart, but you might think about that. Okay. So anyway, a smooth, this generalizes the notion of smooth. Let me say a little more. I'm not really, so we use these properties in our proof, but I'm not going to try to fit that in today. Maybe Alex will do that part of the proof. I don't know, but I do want to get some intuition about derectifiable sets because they come up a lot of different places. So there's 2 characterizations that are important for us. So the first one is a little technical to write down. It says that if you have, the idea is if you have a Lipschitz, so Lipschitz doesn't, you can be far from one to be injective, right? Okay, so there's no kind of injectivity in a Lipschitz mapping. So you can kind of compress things, collapse things, all kind of stuff. It says that if you have a derectifiable set, then it's almost the countable union of isometric images of bounded sets from RD. Okay, so what it says is that if A is derectifiable set. Yeah, I should put that out. Then there's a countable collection of sets Ki back here and almost isometric mappings. So these are almost flat, right? Because it says for any epsilon, we have a bi-Lipschitz mapping for each one of these Ki's, mapping Ki into RP. So each one of these pieces is almost an isometric image of a compact set from RD. Then you can decompose A into these disjoint compact sets, almost isometric sets, plus a set of HD measure 0. So this is this idea that a derectifiable set is almost countable disjoint union of pieces from RD. There's another characterization that's important for some of our machinery, and that is that a compact derectifiable set or a compact derectifiable set, then what's called the d-dimensional Minkowski content agrees with the d-dimensional Hausdorff measure. And this gives you some more structure on the set. Let me just quickly give you an idea of what this is saying. So if you have, say you have a one rectifiable set, like a nice curve, and then I should have said this A of epsilon means the epsilon neighborhood in RP. So if we're in R3, then the epsilon neighborhood will be something like this. And so for a nice set like this, then the volume or the p-dimensional Lebesgue measure of A epsilon is going to be almost what? It's going to be almost the d-dimensional measure of, so in this case, the length of A. And then we take the ball in the with codimension in the codimensional space. So we take these kind of balls. So this will be LP. Guess I'm putting P up here of the ball. And this is in the codimension, sorry, so that's P minus D. So it's saying that in this case, in 3 dimensions, this will be saying that this tubular neighborhood has volume approximately, this is not equal, this is approximately, equal to the length, the one-dimensional length of the set times the volume of the circle of radius epsilon. And as epsilon goes to 0, this approaches, this is the definition of the Minkowski contact. And it's equal to the d-dimensional Hausdorff measure. And so that's, this is our main theorem. This is the theorem that, this is what at least got me started in this business. And this was kind of going to, like Ed talked about, going to lunch with Steve Smale. I made the mistake of when I was supposed to be writing a grant proposal, I went to a seminar that a new colleague at SAF gave, talking about these point things. And so instead of finishing that grant proposal, I started thinking, oh, these problems seem easy. So I was mistaken. But anyway, so this is our result. And we'll have several variations on this that I'll talk about. So it says that when S is bigger than or equal to D, so we're in the Riesz kernel. So we're in the case when the Wiener constant is infinity, the hypersingular case, and we have a D-rectifiable set with positive measure. If it's 0 measure, then things become trivial here. The results, it becomes kind of a vacuum case. Well, with positive measures, then what we get is that the limiting distribution is going to be uniform with respect to Hausdorff measure restricted to the set. So if you have a smooth 2-dimensional surface, then you're going to get uniform distribution as the limiting density. And this is this short range property, and I'll say a little more about that. So this happens for bigger than or equal to D. When S is bigger than D, then instead of having an n squared term, the dominant term is n to the 1 plus S over D, which kind of makes sense. If you think about the point energy, the energy of a single point summed over all the other ones, and the nearest neighbors are going to be on the order, the distances are going to be on the order of n to the 1 over D. Then when you plug that into a Riesz kernel, you see that the point energies are going to be on the order of n to the S over D. You have n such point energies. So this is the right scaling. The only place that the geometry of the set comes in at this level is just in terms of its size in terms of d-dimensional measure, the Hausdorff measure. Of course, yeah, so this, and then there's a constant CSD that is important for us, okay? And so, and this we'll talk some about, and then there's some lower order terms that we don't know much about yet. Yes. Which one? Right here. Okay, so let me say, so this one is a little bit embarrassing in the sense, this is the boundary case when S equals D. It's the case of like a harmonic sum when you're summing over the integers. It's the boundary case for the zeta function, for example. Okay. And for reasons that are probably just defects in our proof, but maybe we need some more structure. I don't think so. I think it's defect. We have had to require more structure. So we need kind of more structure on the embedding space. It can still be kind of a fat Cantor set, but we need that A is contained in a C1 manifold. Okay. Anyway, but in that case, this coefficient that's taken, so two things, instead of being n squared, there's a log n term that's coming kind of from this harmonic sum kind of property. And we know, in that case, we know what the constant is. And it's because in this case, this is kind of like a harmonic sum. It's short range in one case. It's not like an integral, but it's long range on the order of n to the 1 over d. Those things don't, the exact local structure doesn't really matter. Okay, so anyway, I won't talk much about that one because we haven't gotten back to it. So let me just give a little outline of where we're going to do. So what we'll first do is prove that the limit exists for a nice flat problem. So for us, the nice flat problem will be the unit cube, and we'll use a scaling, self-similarity and scaling result. And we've seen this, so we were excited about this, but we've also, about the same time as we were doing this, Gruber used a similar kind of argument to establish a result for best quantization that I'll say a little bit about. So this rough idea probably has been used other places. Right now we're developing kind of a general theory of short range potentials that takes it where we can apply this strip. So I am going to prove this part because I like this proof. Then once we get, then the part that I am going to skip, maybe I'll hit the exact worst combination of saying too much but not enough. So I'll try about then. Once you've got it for the flat case, we take advantage of the short range property together with some of these properties of derectifiable sets and techniques from geometric measure theory to first expand from the unit cube to general compact sets in RD. And then we do this for embedded sets. We then we use the characterization of derectifiable sets as being almost isometric images from RD to finish that. So I'm not going to say much beyond what I've done. Anyway, I like this group. So the problem is with these, and maybe I think there are other ways. I'd be curious, to establish these limits. The problem is you you can show that the lim sup and the lim m's are both finite and positive. But you need something to pull them together. Okay. And for example, fractals, self-similar fractal sets, that's a problem. The pulled together part doesn't happen. Along certain subsequences, the lim sup and the lim m's are different. And so here is the idea. First of all, we're going to think about take an optimal configuration of, in this case, endpoints. And then we're going to map them, we're going to scale by 1 over m, map them into disjoint subcubes. There'll be m to the d of these. We're going to include a little shrinkage, that's the constant gamma, to make them separate. And then we're going to say, okay, this one may not be optimal, but this energy, the energy of this has to be bigger than or equal to the minimum energy for m to the d times n points. And then we'll use that to tie things together. So, okay, so here we go. So the energy of the cube with this many points, it's going to be less than or equal to the energy of this particular configuration that came from n. When we sum the energies here, we'll first sum the subcube energies themselves. So they're m to the d of them. The subcube energies these are just translations of one another. So it gets repeated m to the d times. There's a scaling of gamma over m. And then we have to worry about cube-cube interactions. And it's not hard to show this, and this kind of estimate comes in a lot when you're doing the short range, that the cube-cube interactions are, okay, there's a little 1 minus gamma that's separating here. Anyway, there's a constant 1 minus gamma to the minus s. And then m to the s plus d times n squared. So they both have, so this is an estimate on the cube-cube interaction. It's not hard. In fact, I did have this as an exercise, but I don't even think it's worth that. Now we use the scale invariance of this energy to pull out this factor to the minus s. So if you scale a set with this, comes out to the minus s. This term is this thing to the minus s. Both of these terms have this m to the s plus t term. So we get that this minimum energy is bounded above by, so now I've divided both sides through by m to the s plus d. That's right here. Now we're relating the minimum energy of m to the d endpoints to the minimum energy of endpoints. And I've got the right, this cardinality and this cardinality are the same. And we have this term that's left over. Okay. But this guy will be of lower order. Okay, because this is to the minus 1. So as n goes to infinity, this part will, or what I should say is this s over d minus 1 is positive. So this will go to 0 as n goes to infinity. In any case, when we take a value of n that's between, now we're going to take m to infinity, which is the m is our scaling for the self-similarity. So if I take it, so I've got kind of estimates along this subsequence. If I take a cardinality between these two, then, okay, so the energy is monotone in the number of points. It's because we have a positive kernel, you add terms, energy has to go up. So if I replace this with an upper bound right here, the numerator grows. And similarly, if I replace this with this, then the denominator gives me a larger value. And I've kind of here, you see this m minus 1 is here, the m. So I skipped a step there. So this is just using the monotonicity of the numerator and the denominator. Oh, I think I was supposed to have this in there. So this is supposed to be right there. Less than or equal to. This part, I think I messed it up.
In the second step, you use the first inequality to the PS. PS of UD and the
Yeah. The first one
so
here
and
and
now you
goes.
use the first thing on the slide.
What's that?
Yeah.
Yeah.
Now you use that, you insert it, and
Yeah.
the last line.
Yes, great. So let's skip the middle one. There we go. Yeah, I think the middle line is missing something. Great. Yeah. You're right, completely. Yep. And so now what happens as m goes to, there's a slight subtlety. We'll first take n to infinity. So as n goes to infinity, m goes to infinity. As n goes to infinity, m is forced to infinity. This goes to 1. This has no m in it. So capital N was fixed. It was the number in our original. Okay. So this goes to 1. And we have this result. Now we take now we'll take n just a second. Get this result. Yeah. So the limb suit, the limb suit is bounded as n goes to infinity. The limb suit is bounded by this quantity. Therefore, the limb suit will be taking n along a sequence going to infinity. We get the length right here. And then at the end, we take gamma to 1. So let me just make sure I say that right. So this holds for any n. I can take this n along the sequence going to the limb m. And because on this side, capital N has disappeared. The gamma is still hanging around right here. I can't take it, but now I can finally take gamma to 1. Okay, anyway, that's more than I wanted to say. I'm going to skip. There's so there are some nice applications of geometric measure theory to, I'll say a little bit. Okay, so the same argument that we just did for a cube works for, say, a union of cubes with disjoint interiors. Okay, and so that is so we can establish when A is a finite union of cubes with disjoint interiors using the same kind of idea. Then if we extend to sets which have boundary measure 0 or Jordan measurable sets, And we do that by approximating such sets from the inside and outside with finite units of cubes. And then kind of a surprisingly tricky part is to extend from Jordan measurable sets, in other words, nice sets whose Lebesgue measure of the interior is the same as the Lebesgue measure of the closure. To go to general compact sets, we need this structure we get from the Minkowski content. Okay, so that's a bit tricky step. And there's a bit of measure theory and Vesicovich covering comes in, and I'm not going to, anyway, we've got that in sections 8 and 6 and 8-7. Missing a slide. Where is the slide? Okay. Well, then the final part is to use the Federer result. I don't to extend to embedding sets using the fact that a derectifiable set is almost made up of disjoint copies of sets from RD. So that slide may pop up in a minute. Okay, I want to say a little bit more about this constant CSD because this is for us kind of a big problem. So MMRS, Ed was going to talk a little bit about the hypersingular case on curves. So this is a paper, Minuscule, Martinez, Finkelstein, Rachmaninoff, Sapp, about energy on rectifiable curves. And from these results, we get that CS1 is the Riemann zeta function. We'll say a little bit about why that is, but for the Riemann zeta function, classical Riemann zeta function. So this really reflects the fact that energy minimizers, when S is bigger than 1 on a curve, are almost equally spaced. Okay, and then you, from one point to the next, you begin building up the Riemann zeta function. Now, in certain dimensions, for example, 2, and then we'll mention a few others, it appears that minimizers for our flat case are what are going to be approximated by lattice configurations. By a lattice, I mean a Bravais lattice, and I think physicist language. By a lattice, I mean the integer linear combinations of some basis of RD. And the Epstein zeta function for a general lattice is going to be sum over all the distances raised to the minus s, except for excluding the 0. And so if you took a point, say right here, and then began summing over, there would be 6 nearest neighbors, so you get 6 times this nearest neighbor raised to the minus s. The next nearest neighbors, there's again 6 of those, plus 6 times that distance to the minus s. You sum over, so you take a point and then sum over all those. When s is larger than d, it's easy to see that those sums are convergent. It's like the one-dimensional in the US, we would call it, in calculus, we would call it the p test. If you sum 1 over k to the p, that's finite when p is bigger than 1 and infinite when p is less than or equal to 1. So this is like the lattice version of that. These sums, these lattice sums, are absolutely convergent when this Riesz parameter is bigger than the dimension of the lattice. Okay. Then it's not, so I'm not going to do it. Maybe I thought I had this as an exercise. So kind of write, I'm not going to write. So I should say exercise. Show that CSD is bounded above by this, by the zeta function for this lattice. Oh, and I should have said, here, this is the co-volume of the lattice. So this is the co-volume is the volume of any measurable fundamental domain. For example, kind of a canonical fundamental domain is going to be A applied to 0, 1 to the D. That parallelotope is kind of a canonical fundamental domain. The volume of the lattice is the co-volume is the volume, I'll say volume or the Bayes measure of omega lambda, which is going to be the same as the absolute value of the determinant of A. So once you scale out the co-volume, CSD is bigger than, is bounded above by this. And if the local structure for minimizers is really equal, is given by that lattice, then that's equal. So I'm not going to try to make that more precise right now, but so in one dimension, it's saying that the only lattice that we have in one dimension up to scaling is the integer lattice. And it's saying that in one dimension, a lattice, the minimizers are lattice configurations. And in other areas, this also has come up. It's for us, the biggest open problem is that CS2 is given by the lattice. It's given by the Epstein zeta function for the hexagonal lattice. And so we see this in images. It comes up. It's an assumption in like two-dimensional solid state physics that this is the general ground state in two-dimensional solid state physics, whereas in 3 dimensions there are many competing crystal structures. Now, because of recent results of Cohn, Kumar, Miller, Radchenko, who I think will be speaking this afternoon at Vyazovska, a consequence of their universal optimality results that the E8 lattice is optimal in 8 dimensions, and the Leach lattice is universally optimal in 24 dimensions. That tells us that in dimensions 8 and 24, that tells us that in fact this is the zeta function for this lattice. So we know CSD in dimension 1, 8, and 24. Okay, so we're pretty sure we know it in 2, but proving that has proved to be difficult. Graduate student Nate Tenpass is here. We were working on some smaller cardinality problems related to this conjecture. This group, Cohn, Kumar, Miller, Radchenko, and Vyazovska have been working on this for a while. So maybe they will announce something soon. We've got another approach that we hope they don't announce too soon, but who knows? Okay, so I do want to just finish up with some pictures. So here is some near optimal. So these are numerically, David Zhang was a great undergraduate. He's at Stanford now. Worked on this as a summer project. This is showing the Voronoi tessellation of what? On the left, 4,000 points, on the right, 10,000 points on an algebraic surface. This is using the S equals 3. So this is a 2-dimensional surface. So we are well in the hypersingular case. The points are the kind of centers of these little Voronoi cells. And they are you see the uniform distribution. You also see, so they're also, the Bornholm cells are colored by the number of nearest neighbors. And when you're in the midst of these regions that are all hexagonal, not only are they hexagonal, but if you look at kind of the nearest neighbor distances, the hexagons are all extremely regular. They're all have nearly the same in radius. The histogram is beginning to model the histogram for the hexagonal lattice in the plane. So you see, especially for the small distances, that kind of coalescence of the histogram. So this is reflecting the fact that CS2 is got to be the zeta function for the hexagonal lattice. The geometrically, our result is saying that in the average sense, we have to have most points are going to lie approximately in, at least their local neighborhood structure will be hexagonal. Okay, that means, so out to a finite number of steps. Okay. I wanted to say a little more about the Womersley conjecture, and it seems to me right now that this n to the, so that the Womersley, what we're calling the Womersley term, since he was the one who convinced us numerically, n to the 1 plus s over 2 log n. It seems that this is a term that's a combination of a bulk term that comes from deforming the lattice locally. So there's kind of a bulk term that we don't really understand well, together with some kind of thing that happens as these patch together. Okay, so
Well, questions not directly related to this, but so like these scars, they look like somewhat one-dimensional-ish.
yes,
Is this true in all dimensions? Like if I look at say more dimensions, do they still form straight?
that's a great question. It probably they're probably going to be more surfaces where, but that's not based on any. So there's something about where lattices come together. So if the lattice structure or a periodic structure of some kind of thing comes together, but then it's forced to kind of break because of curvature.
Yeah.
Okay. And so, but I did want to say that these pictures, we're doing this with s equals 3. But if you did it with s equals 1 or the log, if you're in the integrable case, you still see very similar pictures. And that's because there's a second order term that particularly Mersha and Hardin and Sylvia Sabati, and I've got a list of names here, have subtracted, after you subtract off the long range effect and get a renormalized energy, or then that renormalized energy becomes more like a short-term problem. So anyway, on the sphere, we don't see, whatever the differences between the short range and long range, they're subtle. They're going to be reflected, not in what we're seeing. These kind of grain structures. It is true, like when Rob, he's a much better optimizer than me. You'll still see scars like this. The length of the scars will be somewhat smaller because his optimization, but qualitatively, there's not a huge difference. Okay. Anyway.
There's no conjectural form to it, like that. It really forms some point process or something like that.
Yeah, we're we're embarrassed that we don't have that, but it's an area of active research for us. And also in David Nelson, Mark Bowick, others, Alex Travis said, that there are a number of physicists that kind of work on crystals on curved surfaces, trying to understand properties of them. I think this is, yeah, this was, okay, so oh, I did want to leave with this open question, and I'm hoping that we can work some on this, is that, so Fetterman and Sandier extended the kind of flat space estimates for the next order term to prove the existence of the next order term for the log energy. And we're interested in generalizing that from next order estimates that are mostly in Euclidean space in different settings to embedded cases. So we don't, so for example, we don't know, although it's got to be that the CSD n to the 1 plus s over 2, so the term n to the 1 plus s over d, this term now becomes a second order term when s is less than d, because this is of lower order than the n squared term. And so this has got to also appear for the sphere and other embedded manifolds. I'll stop there. Thank you. Are we done?
If there are any questions, otherwise,
I guess so you mentioned that it looks a bit like Schramm-Lerner.
Say that again.
It looks a bit like Schramm-Lerner.
I don't know Schramm-Lerner.
Schramm-Lerner.
What's that?
Yeah, Schramm-Lerner is like conformally invariant curve.
Okay, I'd love to talk about that. There are some. Yeah, that would be cool.
I mean, it's already there. You have like
I definitely think there should be a nice PDE model that is dependent on the cardinality, and that the regularity of the solution will break, and I'm sure, you know, Professor Prout may have better ideas about how to model such things.
I think that's just pictures.
Oh, you don't think this is?
I mean, I mean, that this. I mean, looking at the, of course, this is kind of, this looks like topological, right? This is, this is related to crystal established physics and so on and so on. People looked at these pictures for such a long time. What do you get out of something? What does it tell you? I mean, you don't know whether this is, I mean, as we heard this morning, this could be one, it's not clear whether the configuration that you have here is the global minimum.
Yeah, so
it's probably not even true.
Oh, no. This is not even probably a local minimum. But we see that when the energy gets close to the global minimum, there are still generic properties that all the configurations, at least with high probability, have. And so, okay, but I'll stop there. Yes, go ahead.
Comment on that open question. I guess it's also of Sandier fatty and facts that mean are about the expansion of the rotation function.
Can you speak louder? I can't hear. Can you speak louder?
So I guess that the results by Sandier fatty and Traxor fatty, the results that mean by Sandier fatty and Traxor fatty are about the expansion of the rotation function and about energy. So I guess that in order to generalize those resources to that surfaces would be a kind of normalized energy on Euclidean systems.
Yes, that's true. And and there are, so you need to subtract off the long range effect in a way that then leaves you the next term.
Probably not to subtract the long range effect, but we make it local with the hand of the screen.
Yeah, but for me, that is close to subtracting off the long, whatever you're doing, you're subtracting off the long. You're needing to account for the diagonal terms that you're excluding. So anyway, we've got exponents here. So, yeah.
Yes, so thank you, and then we are going to continue tomorrow, right?
Yes. Unless everyone says no. Yeah, I've got more slides.
Groups and trifurcations. You looked at some. You have. You asked. Yeah, but